Okay, let's go ahead and get started on this one. This is an induction problem, electromagnetic induction. And we're given a solenoid. When we look at the solenoid, notice that they're giving us a front view of it, but it is something that you'll want to kind of pop out into 3D into your brain. So the dash lines on the solenoid wire are meant to be the lines that go back behind that interior area there. Okay, so have that in your mind so you can be applying right-hand rule. What I want to add to the permanent magnet is the field. So question A asks us about magnet 1. So I'm just going to look at that magnet for a moment. And I want to draw the magnetic field from that due to that magnet, right? So let's just think about these are the field lines due to that magnet. They're looking like this. Okay, so there's my B field. And I draw that because I want you to think about the B field lines. When we're considering flux, flux is, right, we can conceptualize flux as the number of B field lines permeating through an area, a defined area. In the case of the solenoid, it's the interior area of the solenoid, okay, or the area, um, you could say like bounded by by one spiral. So in part A here, here's our field. Okay, I'm going to mark this here. This is B1, the B field due to magnet 1. And it's being moved away from the solenoid. So let's also label that. So I have a velocity here. This is important. That's directed to the right. So they want to know, is there an induced current? And if so, what is that current? So yeah, there is an induced current. So starting part A, we know that yes, there is an induced current. How do we know that? Well, as long as you have, sorry, that's a weird D. As long as you have change in flux, remember this is magnetic flux that we're talking about, over time, non-zero, and we're going to have that, right? The magnetic flux is going to be changing as this magnet is moved to the right. It's going to be decreasing. The field that permeates the solenoid will decrease as you move the magnet to the right. The magnet gets farther away from the solenoid. So as long as I have a non-zero flux, then I have a non-zero EMF that's generated. That's what Faraday's law tells me. So as the magnet is withdrawn, the leftward phi decreases, right? We can see that. So I'll write this out. So basically, as the magnet moves to the right, there, I can say that the B field, the B in the solenoid, and more importantly, the flux, right, in the solenoid decreases. So we have a decrease there. And remember, it's any change that causes the EMF. It doesn't have to be an increase. It's just all about the change. So the solenoid was going to oppose that change. Remember, this is what happens here with induction is that the idea that nature doesn't want that change to happen, right? The solenoid is going to oppose the change and it's going to produce current to produce a leftward phi, right? It doesn't want that B field to be reduced. So it's going to say, I'm going to produce a B field myself to kind of fill in the gap of that B field decrease. So think about what that's going to have to be. Use right-hand rule there, right? What is the current? What direction will the current have to be in order for you to produce a B field that's directed to the left? So I'll say here, so the solenoid will produce a B field that's directed to the left. All right, so then it's up to you to look at right-hand rule and ask yourself, what direction does the current have to be in order to produce that B field? And I can see that the current will flow And here's where you need to pop out the solenoid into 3D, right? The current has to go up the front of the coils and down the back of the coils. If you do that with your right hand, you'll see your thumb will point to the left, which will be the B field due to the solenoid. So in order to get that, the current has to flow from in the same direction from right to left through R. Okay. So we figured that out. Let's go on to part B. Part B asks what about magnet 2? So magnet 2 is the one that's kind of up above the solenoid there. And I'm going to draw in that B field as well. So this B field would look like this. It has symmetry in this way. Looks similar to the other B field, but so this is B2. All right. Now consider this question here. Is there an induced current as magnet 2 is moved away? If so, what is the current direction through resistor R? So now we're moving this away. This is going straight up here, right? Going straight up. And we have really nice symmetry in this case. And as long as I move that magnet straight up, think about your flux. Will your flux change? Will your flux change through that solenoid? The answer is no. So this one's no. And we won't induce current. I'll say here, due to symmetry, and you can draw a few pictures if you want to kind of be able to see it in your mind. It's important that this magnet is moved straight up there, perpendicular to the length of the solenoid. Due to symmetry, um, here, right? As long as I remain on the vertical path here, I have no change in flux here. And furthermore, what's even more important to kind of look at, I guess it's important to look at the change in flux, but if I really look at the total flux, right, what would be the flux through the area of my solenoid for this magnet, magnet 2? Actually, what we also see that the flux itself is equal to 0. And you might be saying, well, no, it's not. What about those curved field lines? And I would argue that those curved field lines are going to always have an opposite pair on the other side, right? So when I sum up all the flux there, it's actually going to sum to 0. But the important part is not that the flux is 0. The important part is that the change is 0 when it comes to Faraday's law. So as long as the magnet remains on a vertical path there, then we will not have any current that's induced in the coil.